Hi, my name is Talha Abdul Qudus, and today I'll be presenting my master's thesis on generalized risk control for multi-label chest X-ray classification. Imagine you're a radiologist nearing the end of a long shift. You get this chest X-ray. Your new AI system instantly analyzes it and flags potential conditions with high confidence, including atelectasis. This is great, it's fast, and it correctly identified a key finding. But what this AI doesn't tell you is that it completely missed a subtle concurrent finding: infiltration. So the question is, how would you know? When the model presents its results with such certainty, how can you trust it not to make a clinically significant mistake? This is the core problem my project addresses. We need models that don't just predict, but can provide a reliable guarantee about its risk of making such a mistake. To address the clinical need for trustworthy AI, I implemented and compared three frameworks which form a hierarchy of increasingly powerful statistical guarantees. First, the baseline inductive conformal prediction. It works by calculating a nonconformity score, which is a measure of how strange it is, for every point in a holdout calibration set. It then finds a cutoff point, like this 90% Q hat, and uses that as a universal threshold to guarantee marginal coverage. This threshold is then used to determine which classes exist in the prediction set. It's simple, but it doesn't know anything about specific clinical risks like false negatives. The next framework, conformal risk control, is more sophisticated. For every possible threshold, which we call lambda, it calculates the average risk, such as the false negative rate, on the calibration set. This gives us a risk curve. CRC then finds the optimal lambda by identifying the point where the empirical risk first drops below our target alpha, say 10%. This gives us an inexpectation of the FNR bounded by alpha. However, it relies on this risk curve being well behaved and only guarantees performance on average. As you can see, quite a few results here are past our target alpha. Finally, Learn Then Test provides the strongest assurance by reframing the problem as hypothesis testing. Like CRC, it starts with the risk curve, but for every point on the curve, it performs a statistical test of the hypothesis: is the true risk above our 10% target alpha? It calculates a p-value for each threshold. However, we can't just pick all the p-values below our target. When you run thousands of tests, you're bound to get some lucky results and accidentally reject a hypothesis. And in this situation, rejecting hypothesis means that the risk is controlled. To prevent this, LTT applies a family-wise error rate correction to control the overall probability of making even a single error, say a 10% error rate called delta. All the thresholds that pass the safety check, meaning their p-value is below our confidence level, are collected into a safe set. We can then confidently pick the best threshold from this set, and this provides us a robust high probability guarantee where we can say things like you can be 90% confident that the FNR is below 10%. As you can see, our delta here is incredibly small and most of our values are behind our alpha threshold. And because it's a hypothesis test, it can work with any risk function, not just simple ones. As you can see here, this is a non-monotone risk compared to CRC, which were restricted to monotone risks. My key contributions are fourfold. I'll show that the baseline method is clinically unsafe, that CRC provides a significant improvement on that LTT offers an even stronger, more reliable guarantee, and finally that LTT can control complex risks that are beyond the scope of other methods. To ensure my findings are robust and not just a one-off, I conducted a systematic evaluation. I've implemented this pipeline to test all three frameworks across several large datasets and several pre-trained deep learning models. Here we quantify the clinical risk of the standard baseline. Although ICP guarantees that each pathology is correctly included in its prediction set about 90% of the time, this graph on the right shows the clinical reality. The false negative rate, the fraction of misdiagnosis, is about 43% for ICP. This is far too high for any clinical application and confirms that a simple coverage guarantee is not enough compared to CRC, which keeps its false negative rate around the target 10%. My implementation provides a command line interface for controlling the dataset and model used. Here's a sped up demonstration of generating the empirical risk graph for CRC, specifically the ResNet model on the PadChest dataset. Next, I compared CRC and LTT on their ability to control the false negative rate at a target of 10%. As you can see, CRC's performance is centered at 10%, but on many trials, the error rate is significantly higher. About half of the results actually sit above our target threshold, which is due to its inexpectation guarantee. In contrast, LTT provides a high probability guarantee, which means its error rate is sharply truncated at 10%, meaning it almost never violates our threshold here. This is a much more robust assurance for clinical deployment, but this comes at the cost of larger, more conservative prediction sets for LTT as it gets pushed down this graph. The big advantage of LTT is its flexibility. It can control complex, non-monotone risks like the false discovery rate, which are the proportion of false alarms. This is something CRC can't do because that's only restricted to monotone risks. As the graph shows, LTT successfully controlled the FDR at multiple user-specified levels. This is clinically important for ensuring that the radiologist can trust the system's positive findings and not suffer from alarm fatigue. So let's return to the clinical dilemma from the beginning. The AI assistant confidently identified atelectasis but missed infiltration. How do our framework solve this? The baseline ICP, as we established, is unreliable and it fails. But the LTT framework, configured to control the false negative rate, successfully produces a prediction set that includes both pathologies. It solves the dilemma by providing an output the radiologist can trust, backed by its robust statistical guarantee. In conclusion, my project provides a thorough comparative evaluation of risk control frameworks for medical AI in X-ray classification. My findings, validated across multiple models and datasets, show that for safety-critical applications, the high probability guarantees offered by Learn Then Test are the more robust and reliable choice. ICP is unsafe for clinical use due to its high FNR. CRC, while it can control for FNR, only controls it on average, meaning that for certain scenarios, it's not suitable for clinical use. This work confirms that it is possible to build trustworthy AI systems that provide strong generalizable safety assurances. Building on these findings, this opens up other avenues for future work. One is the simultaneous control of multiple risks using LTT. A clinician has to balance the risk of missing a disease, controlled by the FNR, with the risk of too many false alarms, which is controlled by the FDR. My work controlled this one at a time, but future work could leverage a multidimensional lambda with LTT to create a single system that is calibrated to control both risks simultaneously, directly optimizing for clinical utility. And this concludes the presentation. Thank you.